So, how is it that we know so much more about the galaxy than Kapteyn or Shapley? The main reason that we have more information about the galaxy we live in is because they were using visible light to make optical observations, and we have access to the entire electromagnetic spectrum. And so, in this clip, we're going to look at the Milky Way through several different bands and emphasize what it is that they teach us, each of them about the Milky Way, and then later we'll put together all that information and see what we know about the galaxy. So here's the multi-wavelength approach to the Milky Way, and each of these images is an image of the entire plane of the Milky Way folded around, unfolded, so that the center is Sagittarius. The direction to the center of the Milky Way is centered in the images, and we're seeing all of these, except the bottom, are false color, and we're seeing images of the Milky Way as it appears in various frequency bands. And we'll start at the lowest frequency at the top. These are radio waves, 408 kilohertz. The radiation at these wavelengths is produced mostly by relativistic electrons propagating in the galactic magnetic field. So we see that there are a lot of emissions near the center of the galaxy, and we see some localized sources. The source on the left is Cassiopeia A, the supernova remnant. We talked about it, and the emission from there is, in fact, so brilliant that if you look carefully, you can see a sort of triangle shape around it, which are the diffraction images of the legs of the antenna, that is the radio antenna used to produce the image. And so this gives us a map of where high-energy charged particles are found. At a slightly higher frequency and a slightly shorter wavelength, at 1.4 gigahertz, we have an extremely important measurement. The wavelength corresponding to 1.4 gigahertz is about 21 centimeters, and this is an important frequency because it allows us to see clouds of neutral atomic hydrogen. Now, neutral atomic hydrogen is difficult to see because unless it is very hot, the atoms are mostly in the ground state, and the frequency or the wavelength corresponding to excitation from the ground state to excited states is ultraviolet. So cold atomic hydrogen has absorption spectrum in the ultraviolet, but there's not enough necessarily ultraviolet light to observe it. On the other hand, it can both absorb and emit, even at the relatively cool temperatures we're talking about. At this wavelength of 21 centimeters, this is not an atomic transition where the electron jumps from one energy state to the other. In fact, what this is the frequency with which the electron precesses. The electron carries angular momentum, intrinsic angular momentum, and a magnetic moment, and the electron's angular momentum precesses around the direction perpendicular to its orbit. So just like the Earth's axis wobbles as it orbits around the sun due to gravitational tidal effects, in this case, the electron's axis wobbles as it orbits the proton due to electromagnetic effects, and the frequency with which it wobbles or precesses is 1.4 gigahertz. And so this is a low frequency. At relatively low temperatures, these atoms are excited, so they emit these radio waves. Two great properties of this. One is it's emitted by neutral hydrogen, and two, because it is a radio wave, dust and gas clouds do not obscure it. So when we look at 21 centimeters at the galaxy, we can see through the clouds and the dust, and we can see the big gas clouds themselves. And you see that the 21 centimeter image of the galaxy shows us that hydrogen is scattered throughout with, of course, increased density near the center. Being able to observe the neutral hydrogen clouds, atomic hydrogen clouds in the galaxy is going to be extremely important. Moving to a higher frequency, a still shorter wavelength, the 2.7 gigahertz, notice that the wavelength of the 21 centimeter spin transition is rather sharply defined. You change wave frequency, you don't see the atomic hydrogen anymore. 2.7 gigahertz, we're looking at emissions by ionized gas and also fast, albeit not relativistic, electrons. And again, we see Cassiopeia A as a source. We see the center of the galaxy as a source. So these, again, are energetic, localized sources producing these. And There is also a sort of galactic emission, but that's been subtracted to exhibit these point sources better in this picture. The middle pane is 115 gigahertz, and this is again an important one. In fact, this corresponds to the energy of a transition in carbon monoxide. Carbon monoxide? Where would we find carbon monoxide? Turns out that carbon monoxide, while rare, is a very useful tracer molecule. Its concentrations in various regions of the galaxy closely trace the concentrations of molecular hydrogen. Where you find molecular hydrogen clouds, there are small trace concentrations of carbon monoxide. Following the carbon monoxide, we get a mapping of molecular hydrogen, and we see, as I said, that molecular hydrogen is constrained to the plane of the galaxy, and we also see that in certain places there are a broadening of sort of places where the hydrogen clouds spill out of the plane, and we'll see those again in a second. At a slightly higher frequency, between 3 to 25,000 gigahertz, these are infrared emissions, and these far infrared emissions, in fact, are given off. We see that there are not many point sources, but sort of a continuous emission from the entire galaxy. Furthermore, we see that these emissions seem to track the H2 emissions, and where there is added H2, where there are molecular hydrogen clouds, there is this infrared emission. Indeed, at this wavelength, we're basically observing the dust. It is extremely important that we can see the dust in the Milky Way, because then we know what we need to subtract, because we can use this tracing of the dust and of the molecular hydrogen to figure out what the extinction is and try to reconstruct the correct luminosity of objects as seen through the dust. And notice, as I said, that the dust tracks the molecular hydrogen rather well. The image below that is a higher frequency, shorter wavelength yet. This is the near infrared, and in the near infrared, dust is not hot enough to glow. What we're mostly seeing is the emission of stars. Which stars emit a lot of infrared radiation? Red stars. Which stars emit most of the infrared radiation? Giant red stars, red giants. And so we're looking at cool giants here. We see, in fact, that we're seeing point sources, and only towards the center of the galaxy, we're seeing sort of the far side of the galaxy in the center. In that direction, we see distant stars melded together into this great big glow, but on the periphery, we're actually able to resolve individual sources. The important thing is that we can see these bright stars in the infrared through the dust, because remember that scattering and absorption in dust is highly frequency dependent. The high frequencies scatter more, and it turns out are absorbed more. And so looking in the infrared, we can see through the dust and distinguish the stars that are behind it. Stars that produce lots of infrared will, of course, be more visible in this wavelength, but we can see through the dust. These are all the things that Kapteyn and Shapley did not have at their disposal. At the bottom, we finally see a visible light image of the Milky Way. This is the familiar image. We see the dark dust lanes which traverse the Milky Way, where there are clouds of dust and molecular hydrogen, absorbing the light, and we cannot see stars there. Of course, in the visible light, it's the blue luminous stars that dominate what we see, but we cannot see them. And it's interesting to compare the lowest image with, say, the middle image, and see how closely the molecular hydrogen clouds track the gaps in visible light. The gaps in the Milky Way as we see it are precisely at the positions where molecular hydrogen and the attendant clouds of dust are obscuring the light. This is the technology from space observatories and X-rays and gamma rays that I haven't even included here to radio telescopes that was not available to Shapley and Kapteyn, and it's thanks to that we have such so much better a picture of how the Milky Way is constructed. Let's see what it's all taught us.